Today I'm talking about the potential field of a system of charges, and we also discussed about conservative property. The first we talking about potential field of ensemble of point charges. It means in previous section we discussed about the potential field of one point charge. At this time we discussed about the potential field for many point charges. For example, we have 3 point charges, the Q1, Q2, and Q3. And we want to find the potential field at point P. And total potential field for point P is the potential field due to Q1 plus the potential field due to Q2 plus the potential field due to Q3. This is total potential field. And generally, if we have m source point charges, the potential field, total potential field is sigma from m to 1 to n. N is the number of source point charge. Qm over 4 pi epsilon 0 multiply magnitude of r vector and rm prime vector. R vector is field position vector, and rm prime vector is source position vector. At this case, the total potential field, the r vector is the position vector for field. Position vector is the vector from origin to the point. This is origin, and this vector is r vector. This vector is position vector for Q3 source, the R3 prime vector. This is the position vector for Q1 source. This is R1 prime vector. This is source position vector for Q2 source point charge. This is R2 prime vector. So this is sigma from m to 1 to 3 and Qm over 4 pi epsilon 0 magnitude r vector minus rm prime vector. This is potential field to point P is the potential field due to Q1 plus the potential field due to Q2 plus the potential field due to Q3. This is total potential field for many point charges. Next topic is potential field of a continuous charge distribution. A continuous charge means volume continuous charge, and a line continuous charge, and surface continuous charge. Firstly, we discussed about volume charge, the potential field due to volume charge. You know, the potential field is minus integral electric field vector dot dl vector. E vector for volume charge is Q over 4 pi epsilon 0 r vector minus r prime vector a r vector. So I express electric field by spherical coordinate. This is Qm is rho v d v prime. Rho v is volume charge density. Volume charge density. And dl vector is for spherical coordinates, so this dr ar vector plus rd theta a theta vector plus r sine theta d pi a pi vector. This is integral, right? Volume integral. So we can calculate E vector dot dl vector. It's in volume integral and rho v d v prime over 4 pi epsilon 0 r vector minus r prime vector dr. The dot dl is, this is dr dot dr, ar dot ar is 1, ar dot a pi is 0 because ar vector and a theta vector is perpendicular. Ar dot a pi is 0 because ar vector and a pi vector is perpendicular. This is E vector dot dl vector. So this result, input the integral, it becomes potential field point P is minus integral volume integral rho v d v prime 4 pi epsilon 0 r vector minus r prime vector dr. So variable is the volume, source volume, and the r. So this is for integral for this volume, and this is for integration for r. So we can switch this integral because v prime and r are independent. So minus integral volume integral, and integral 4 pi epsilon 0. We let magnitude of r vector minus r prime vector is r bar. This is square, right? So yes, square. So this is r bar square, and 1 dr, and log v d v prime. So the range of r is, we generally the reference voltage is infinite. So this is from infinite to r. So firstly we have to calculate integral from infinite reference potential to r, and this is bar 1 over 4 pi epsilon 0 r bar square dr bar is 4 pi epsilon 0, and minus 1 over r bar from infinite to r. This is minus 1 over 4 pi epsilon 0 r. So this input into this integral, and potential becomes minus volume integral, and minus 1 over 4 pi epsilon 0 r rho v d v prime. Minus is plus, it becomes plus. So the volume integral rho v dv prime. It prime means this is the source volume over 4 pi epsilon 0 r. This is the potential at point P for volume charge. Next is we try to find the potential for line charge, and this is also potential is minus integral E dot dl. The electric field is 4 q over 4 pi epsilon 0 r vector minus r prime vector square, and a r vector. This above is yes, square, and this q is rho l dl prime, and the line integral. Line integral is just a single integral. We above the volume integral is this is a triple integral, and the line integral is just a single integral. So this is, so dl is for spherical coordinates dr ar vector plus r d theta a theta vector plus r sine theta d phi a phi vector. In special case, the line charge is on the z-axis or parallel to z, x-axis parallel to x, y-axis parallel to y. The electric field is rho l over 2 pi epsilon 0 rho a rho vector. But this is a very, very special case for this electric field. So we use general electric field this. So this E dot dl vector is line integral rho l dl prime over 4 pi epsilon 0 r vector minus r prime vector dr. This is the same as the volume, the potential for volume charge. So the result is potential field is line integral rho l dl prime of 4 pi epsilon 0 magnitude r vector minus r prime vector. Yes, this is the potential field for line charge. And similar to the surface charge, the potential surface charge is surface integral. Surface integral is double integral. This is rho s ds prime and 4 pi epsilon 0 r vector minus r prime vector. So the potential for continuous charge distribution has this form. Integral. The denominator is 4 pi epsilon 0 r vector minus r prime vector for free space. The free space is we use epsilon 0, and this is the q. The q can be rho v dv prime for volume charge, volume continuous charge, the rho l dl prime for continuous line charge, and rho s ds prime for continuous surface charge. So continuous volume charge VR is rho v dv prime 4 pi epsilon 0 r vector minus r prime vector, and this is volume integral, triple integral. And the potential for continuous line charge is integral rho l dl prime 4 pi epsilon 0 magnitude r vector minus r prime vector. This is line integral, the single integral. The potential for continuous surface charge is q over 4 pi epsilon 0 r vector minus r prime vector. Q can be rho s ds prime for surface charge. So this is a surface integral. This is the potential field for continuous charge distribution. We take an example. Find potential on the z-axis. The field is z-axis. I draw the graph, and this can be y, x-axis, and z-axis. The field is on the z-axis. The source is the ring charge. The source is ring charge in the form of ring of rho equal a and z equals z. Z equals z, z is 0 is xy plane. The source is on xy plane, and the shape is a ring. So it's a ring. On the ring, we have the charge. So this is line charge. So we try to find the potential field for line charge is line integral and rho l dl prime 4 pi epsilon 0 magnitude r vector minus r prime vector. R vector is the field position vector. The field is located on z-axis. This is field. R vector is the AZ vector. And source position vector is this vector. This vector is rho vector. But since rho equal a, this is a rho vector. Rho vector, and r vector minus r prime vector is c az vector minus a rho vector. The magnitude of r vector minus r prime vector is square root of z prime g square plus a square. So dl prime is this length. This length is dl prime. Dl prime is a multiply d pi. A multiply d pi. And we input this value into the integral. So the potential field is line integral. Line integral is just a single integral. So this is rho l a d pi, and denominator is 4 pi epsilon 0 multiply r vector. This is magnitude of r vector minus r prime vector is the square root g square plus a square. The range of d pi is 0 to 2 pi. So this value is constant in point of view of theta. So it's rho LA over 4 pi epsilon 0 square root g square plus a square integral from 0 to 2 pi d pi. It becomes a rho L over 4 pi epsilon 0 square root g square plus a square and multiply 2 pi. The answer is a rho L over 2 epsilon 0 square root g square plus a square. This is the answer for this question. The next topic is the conservative nature of static electric field. The static means it is not related to the time. It means it's not changed with respect to time, round over round t equals 0. So when potential between 2 points depends only on initial point and final point, it's called conservative field. We need to bring our memory what potential is. The potential is the work done, right? Work done by moving plus 1 coulomb from point A to point B. Work done from 1 coulomb from point B to point A. There are many methods to going from point B to point A. We move 1 coulomb from point B to point A like this, and like this, and like this. And there are many methods to move 1 coulomb from point B to point A. That it means conservative field means when we take any passes, the line integral is the same. It means the potential is minus integral E vector dot dl vector, and it means integral C1 from C1 pass E dl vector and C2 E dl vector, and this equation, when this equation satisfies this field, is called conservative field in static electric field. So in other words, it means the line integral for finding potential is independent of path between initial point and final point. It means once we know initial point and the final point, we can find the potential easily. Just it's dependent on only initial and final point. So this is a conservative the field, and it means when initial point A and final point B is the same, potential between becomes 0 if it is conservative field. We think about we try to find work done plus 1 coulomb from point A to point A. This is the potential is point A to point A. E dl is 0. 0 for every path from A to A. When we take any passes, this result is 0. So this means it is conservative field. So we take an example. Suppose that 0's reference potential is infinity, generally infinity. Find potential at 0, 0, 2. This is the field caused by below sources. This source is nanocoulomb per meter is line charge density. So we draw this situation. This is the y-axis. This is the x-axis. This is the we draw below. This is the y-axis. This is the x-axis. This is the z-axis. The field is 0, 0, 2. This is field. We try to find the potential field at point P, and the source is 12 nanocoulomb per meter. The line charge density on the ring line rho equals 2.5 and z equals 0. This is xy plane. This is similar to above example. So the source is located on the ring. This is ring on the ring. This is a line charge. Line charge is rho L is 12 nanocoulomb per meter, and this is dl. dl prime is d phi. This is a rho d phi. The rho is 2.5, and we try to find the potential due to line charge distribution. So the potential is line integral rho L dl prime over 4 pi epsilon 0 magnitude r vector minus r prime vector. R vector is this vector, 2az vector. 2az vector. The source position vector is this vector, rho a rho vector, but rho is 2.5 and this 2.5 a rho vector. R vector minus r prime vector is 2az vector minus 2.5 a rho vector. So the magnitude of r vector minus r prime vector is r vector magnitude of r vector minus r prime vector is square root 2 square plus minus 2.5 square. This results is input into this integral, so the potential field is line integral is a single integral. So rho L is this rho L 12 nanocoulomb is multiply 10 to the power of minus 9 and multiply. This is dl is rho d pi, rho 2.5 d pi, 2.5 d pi, and denominator is 4 pi epsilon 0 square root 2 square plus minus 2.5 square. And the range of pi is 0 to 2 pi. In point of view pi, this value is constant, so this is we have already known 1 over 4 pi epsilon 0 is 9 multiplied 10 to the power of 9. This is 12 multiplied 10 to the power of minus 9 multiply 9 multiply 10 to the power of 9 multiply 1 over square root 2 square plus minus 2.5 square, and integral from 0 to 2 pi d pi. The answer is answer is 12 multiply 9 multiply square root 2 square plus minus 2.5 square 1 multiply this is 2 pi. The approximated this is 429 unit is volt. This is the answer of this question. And second question is 18 nanocoulomb point charge. Point charge. This is to find potential due to point charge. The potential due to point charge is q over 4 pi epsilon 0 r vector minus r prime vector. So r vector is 2az vector. R prime vector is this vector. Ax vector minus plus 2 ay vector minus az vector. So I draw this situation. The situation is there's a y and x and z, and the field is located at 0, 0, 2, and source is located 1, 2, minus 1. This is 18 nanocoulomb. The coordinate is 1, 2, minus 1. So this r vector minus r prime vector is minus ax vector minus 2ay vector plus 3az vector. The magnitude of r vector minus r prime vector is this square root minus 1 square plus minus 2 square plus 3 square the square root 14. So this is 1 over 4 pi epsilon 0 is 9 multiplied 10 to the power of 9, and q is 18 multiplied 10 to the power of minus 9 multiply 1 over square root 14. This is the answer. And the potential is 9 multiply 18 over square root 14. This is approximated 43.3 voltage approximate. This is the answer of second question. And third question is, this is a line charge. It's located on y equal to 0.5, z equals 0, xy plane, and x is between minus 1 and 1. This is the y, x, and z, and the field is located at 0, 0, 2, and source is y equals 2.5, and x is between minus 1 to 1. This is a line charge. The line charge density is 12 nanocoulomb per meter. So we try to find the potential due to line charge distribution. Potential is line integral rho L dl prime over 4 pi epsilon 0 multiply magnitude r vector minus r prime vector. So dl prime is this is dl prime. dl prime is dx, right? dx, and r vector is this vector, 2az vector. R vector is the position vector of field. This 2az vector. R prime vector is this vector. This vector is this vector adding this vector. This 2.5 ay vector. This vector is xax vector. So xax vector, this is prime, because this is source, plus 2.5 ay vector. This result input the integral. So the potential is line integral. Rho L is 12 nanocoulomb per meter. So 12 multiply 10 to the power of minus 9 multiply dl prime is dx prime, and denominator is 4 pi epsilon 0, and r vector minus r prime vector is 2az vector minus x prime ax vector minus 2.5 ay vector. The magnitude of r vector minus r prime vector is square root x prime square plus 10. This is 10.25. So this input the integral, and this is square root x prime square plus 10 to the 5, and dx is minus 1 to 1. So we calculate this. R vector is 12. This is 12 multiply 10 to the power of minus 9 multiply 1 over 4 pi epsilon 0 is 9 multiply 10 to the power of 9, and multiply integral from minus 1 to 1 over square root x prime square plus 10 to the 5 and dx prime. This integration, we calculated this. I just write the result. I think you can calculate this easily, or you can use a calculator for calculation this. So the result is 16.416 volts. This is the answer for third question. So today we discuss about finding the potential for various charge distribution. Thanks for listening this video, and see you next time. Bye bye.